All right, so today we're going to start our review for the final. So this is going to be a very short video for you guys who are watching on the video, because usually the way we do these reviews is we just go through the previous proofs and the exercises. So I'll basically just ask you the question. You get out a piece of paper and a pencil, okay? And we'll start working through the exercises. Okay, so the first proof that we had after the previous exam was to prove 14.53a. Now actually here is, let's take a look at it up here. 14.53a, 14.53 says let B be a non-empty subset of poset U, and this was, what do we call that? What kind of a relation was that? Ooh, this is good review. What kind of relation is this? Well, the silence is deafening. It is a binary infix operator. That's correct. It's binary infix. So you could say it's in between. You could say this. But what kind of a relation? But what does this symbol? What does this symbol represent? It represents what kind of a relation? Do you remember what kind of relation it was? No. That's not subset. Subset is this. Oh, this is a good review. We need to. This is subset. But what's this? What kind of a relation is this? You remember an example. This is an example of this kind of a relation. This is the less than or equal to relation, right? And this is an example of this. But what is the general? What kind of a relation is this one?
It's RAT.
There you have it. This is a rat relation. This kind of a relation is rat. Good. Okay. So good review. So and what does RAT mean?
Reflexive.
Reflexive.
Asymmetric.
A or anti?
Antisymmetric.
Okay.
And transitive.
Antisymmetric and transitive. Okay. Now you remember on the previous test you had to memorize what each one of these meant. Do you remember what it is? What does reflexive mean?
For all B, B row B.
For all B, B row B. And what about antisymmetric? Now what was the antisymmetric?
No.
Let's hear it. We have to make sure that we get the difference between asymmetric and antisymmetric. This was that table, right?
Yeah.
Remember the table? Here we go. Okay, so here we go. So antisymmetric is for all BC, B row C, and C row B implies B equals C. And that's certainly true for less than or equal to, right? If B is less than or equal to C and C is less than or equal to B, that implies that B equals C. The only way they can both be both less than or equal to and greater than or equal to is if they're equal. Okay, antisymmetric, and this transitive was if. What was this transitive now? If
D row B and B row C.
D row C, yeah. Okay, so yeah, if A is less than or equal to B and B is less than or equal to C, then what do you know? A is less than or equal to C, right? Okay, so this is a rat relation. Okay, so now let's go. So now that we've got that, let's take a look at what it is that we're trying to prove. We're trying to, so the first exercise is to prove 1453a. So it says, let B be a non-empty subset of poset. Now, what does poset stand? No, not power. P-O. Poset. What is poset an abbreviation for? Poset.
Oh.
Poset.
Partial order.
Yes, partially ordered set. Okay, so the PO is partially ordered, so that's a partially ordered set. So, so let B be a non-empty subset of poset. A least element of B is also a minimal element of B. So what implies what? If we want to prove 14.53a, we have to prove that what implies what? B is least implies B is minimal, right? So this is an implication. We have to prove an implication, right? Is everybody with me? Okay, so get out a piece of paper and a pencil. Those guys of you who are in video land there. And here, I gave you a hint. Of course, if I ask you this on the final, there won't be the hint, right? You'll have to know how to do this without the hint. And so here is the hint. It says, so we have to prove 14.53a. Up there it says B is least implies B is minimal. So we start with the antecedent and show that it implies the consequent. Begin with the definition of least. To discover the steps in the proof, work backward on some scratch paper to see if the expression you are headed for. Eventually you will use 14.48.2 followed by range weakening, strengthening. Here are the first few steps to get you started. So we start with B equals least equals by 14.51b, definition of least. Now I gave you a little hint there for universal double trading. All right? So, gentlemen, start your engines. Ladies and gentlemen. How's it coming? Incomparable, right. Incomparable. Yes, not yes, that's right. Yeah, that's the key. Okay, so we're starting with the left-hand side, and so we eventually want to get it to be as minimal. So if we look at the definition of minimal, that's 14.51a, right? Element of S is minimal. Oh, right, and here's where we get that's an it relation, right? C is strictly less than B. But don't we have a range? I thought we used a range weakening. Is this a for all? Do we have a for all?
Yes.
How about 9.10?
That'll do it.
You can get rid of the or.
Yeah.
Okay, good. Yeah, so you got it?
Yeah.
All right. Okay, so next one. Let's take a look at supplementary. Here, so we had a bunch of supplementary exercises. Supplementary exercise S.19 says, which of the following are posets? Well, so what is a poset? Partially ordered set, which is RAT, or reflexive antisymmetry. So, which is the following? For those that are not posets, state the properties that they lack. All right, so equals over Z. Whoa, 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 whoa. Is it?
Yeah. It's reflexive.
Antisymmetric?
Yeah, because antisymmetric says if it has both of them, then they're equal. 1 equals 3 and 3 equals 1. No.
Okay, so, yeah, we need to look at each.
It's antisymmetric, but I was messing it up.
Yeah. For A, okay, we need to see, is it RAT, right? Reflexive. So A equals A. Yes, that's okay, right? What about antisymmetric? So if B equals C and C equals B, that implies
It implies that C equals B.
B equals C, right?
Right, sure. Which, I guess that makes sense.
If B equals C and C equals B, then... Yeah, well, I guess it is. And transitive is, yeah. is A equals B and B equals C implies A equals C. So I guess this is a yes too, huh?
That's just weird.
Because the thing of it is that I know that this is also an equivalence relation. Well, anyway.
Well, it's
How about,
relation.
okay, how about B? So
No,
A,
absolutely not.
so this one's no. So it's not. So which one does it lack? It lacks reflexivity.
It lacks all of them.
If B is not equal to C, and if B is not equal to C and C is not equal to B, does that imply that B is not equal to C?
Is equal to.
Oh, right. That has to imply that B equals C. That's no. And if A is not equal to B and B is not equal to C, does that imply that A is not equal to C?
No.
Now this could be
But
3.
A and C could be the same value.
Yeah, so this is no. So that lacks all three of them. All right. So how about greater than or equal to?
Yeah. I already know who that one is. Sorry, example.
Yeah, so A is greater than or equal to A.
Yeah.
Yes. B is greater than or equal to C, and C is greater than or equal to
Then they're
B implies they're equal. Yes. And then A is greater than or equal to B, and B is greater than or equal to C implies A is greater than or equal to C. That's yes. So that one's a post set. Oh, I put the greater than or equal to here instead of the
Is that not side?
C. Anyway, so now D. So now the operation is does not divide.
I think so.
Okay, A does not divide A. True or false?
False.
Oh, that's false. So right away we know it's not a post set. It's not reflexive. How about this? B does not divide C and C does not divide B. Does that imply B equals C?
No.
No. How about A does not divide B and B does not divide C? Does that imply that A does not divide C?
Maybe.
Oh, interesting.
No, it doesn't.
Is this a no? Do you have a counterexample?
Oh, this is they don't divide each other. So
So can you come up with a
if A is 5 and B is 7
5 does not divide 7
and C is 11.
and 7 does not divide
11.
11? Does that imply 5 does not divide 11? But that's true.
You have to. You have to find one where it is.
Yeah, for the counterexample. 5 does not divide 7 and 7 does not divide 10. Does that imply that
Right.
5 does not divide 10? No.
Yeah, that's right.
So it is, yeah. So, okay, so we did that one. All right. Find two, supplementary exercise S.20. Find two incomparable elements in each of the following post sets. Okay, so find two incomparable elements in each of the following post sets. P012 and subset. All right, so this is S20. S20. So can we find two incomparable ones? What's incomparable?
Means
We have,
if
yeah,
it has a diagram, there's no way to connect them.
right. In other words, we have to find the power set is the set of all subsets, right? So we have to find two subsets such that one is not the subset of the other or the other was not a subset of that one. So
0, 1, and 1, 2.
yeah, 0, 1, and 1, 2. These are incomparable, right?
Or you could have put 0, 2, and
either way. So these are incomparable because neither this is not a subset of this, and also this is not a subset of this. All right, and what about 1, 2, 4, 6, 8 under division? Under divides. 4 and 6 are incomparable. Because 4 does not divide 6, and also 6 does not divide 4. Good. List the ordered pairs. So here's S21. I think maybe what we'll do is we'll just say this one.
Yeah.
All right. List the ordered pairs in the poset relations for each of the following Hasse diagrams. Okay, so now, in order for it to be a poset, it has to be reflexive, antisymmetric, and transitive, right?
Yeah.
So let's first of all, the fact that it's reflexive means we have to have what?
AA, BB, CC, DD.
Right, AA, BB, CC, and DD. Okay?
We also have AB.
And the Hasse diagram, we have to have AB. Let's do all the ones that start with A.
AB, AC, AD.
AB, AC, AD, and then
BC, BD.
BC and BD. All right? And is that it?
Yep.
Yeah, because we did we got transitivity. Okay, so now let's say, let's do part B.
AA, BB, CC, DD.
Right. AA, BB, CC, DD, EE. So those are the reflexive ones. And then
B, AC,
AB, AC, AE, AD,
BE, BD.
BE, BD,
CD.
CD. All right? And then here, we got AA, BB, CC, DD, EE, FF, GG,
AG, AD, AE, AF.
AG, AD, AE, AF,
BG,
BG, BD, BE, BF,
CD.
CG, CD, CE, CF.
That's all of it.
No, that's not all.
So it is.
No, it is. It's so not yet. You're missing 3 more.
Oh, GD.
GD, GE, and GF. Are we good? So, got to be careful there. Okay. Draw the Hasse diagram for each of the partial ordering, S row. Oh, well, this, we should be able, yeah, get out a piece of paper and draw the Hasse diagram. See what you can come up with. There's an A and a B and a C. Then there is
AB,
an AB.
then BC, and an AC for transitivity.
Oh yeah, I guess that is right. Yeah, it is a straight line. Okay, how about B?
It's a V shape.
So AA, BB, CC, DD, and then we have AB and AC,
And
but we don't have
G's off of something
BC.
else.
So we have A, so it's this.
It's a V. And D floats off wherever you want.
So it's A, B, and C, and then D is here. Is that right? That's kind of tricky, isn't it? And why do we not have this line here? Because we don't have AC.
No BC.
No BC, right. B is not related to C, so there can't be a path from B to C. B is not related to C. Okay, and how about those subsets? So you got the empty set, and the relationship is subset. So you got the empty set, so that's down here, right?
Yep. It's a subset of.
And the empty set is a subset of all of those. but
A, B, C.
it's a subset of A and C. Is that right? Like this?
I think there's also a B in there.
Oh, there is a B. So AB, both A and B are going to be subsets of AB, right? And then what else?
A, C.
And so A and C. Like that. Huh?
Yep.
Is that it?
That's what I got.
And even though the empty set is a subset of AB, we don't have a line from AB because in the Hasse diagram it goes from there to there. Let's do S.23. Oh, this is maximal, minimal, etc. Answer the following questions for the partial ordering represented by this Hasse diagram. So here's a Hasse diagram. Got ABC down here at the bottom, and you got all this stuff going up. Right? Okay, got a piece of paper. First find the maximal elements, then find the minimal elements. Is there a greatest? Is there a least? Find the upper bounds of ABC. Remember how the maximal and minimal worked?
Oh.
Hoo-hoo, then this is a good review.
Rather, I don't know the difference between maximal and greatest.
Ah, yes. Shall we review that?
Yes.
Here, let's find. Okay, let's review these definitions. Okay, let S be a non-empty subset of post set. This is 14.51. We do have an image of this. Okay, so let S be a non-empty subset of post set U and this rat relation. Element B of S is a minimal element if no element is smaller than it.
Okay.
No element is smaller.
No elements below it on the diagram.
Yes, no element goes up. Yeah, like there's no element. If this is minimal, there's no element that's below that is related to it. There's no element that's related to it this way. You know. Okay. For B and S, for all C. Yeah. All right. Now, how does that differ from the least? You see, the difference between minimal and least is for it to be least, it has to be related to every element.
Everything else.
It has to be related. In order for it to be least, it has to be related to all the other ones. Are you with me? And then element B is a lower bound. And here, if for all C, C is an element of S, B is rat related to C. So this is kind of similar to least.
It's least, but in respect to certain.
Yeah. Both least and lower bound have to be related. It's for all C, C and S, B is rat related to C. Are you with me? And then the greatest lower bound, GLB, is a lower bound, and if for every other lower bound, it satisfies that. Okay, with that in mind, now let's go and see if we can, and then the flip side of that is, you know, the opposite, it's the maximum is just in the other direction. Okay, so let's go back and see if we can find the maximal element.
L and N.
All right, so A. So how did you get L and M?
Because everything is below them. There's nothing above them.
The maximal,
Which would mean that there's nothing that they're related to on the top.
okay. And how about the minimal?
ABC.
ABC. Okay.
And there's no greatest or least.
And is there a greatest? No. Is there a least?
Yeah.
No. Now, why is that?
Because they don't come to a
That's,
point.
yeah, that's kind of a way, that's a colloquial way, that's an informal way to say it. It doesn't come to a point. Because there has to be one that's related to all the other ones that's the greatest, yeah. So you've got A, B, and C kind of like, yeah, that's informally. Now how about find all the upper bounds of A, B, C?
K, L, and M.
So imagine drawing a little oval around A, B, and C. And the upper bounds have to be related. In order for it to be an upper bound, it has to be related to all of these, right? And have that relation. So so A, the only ones that are common that we have a path from A to A, B, and C up to those are what?
K, L, M.
K, L, M. So are we good? And then what's the LUB, right? The least upper bound. LUB. Let's write it like this. LUB dot
ABC.
the set ABC. These are KLM.
Isn't it just K?
Oh, I thought you said.
It's least upper bound.
Oh, LUB. You're right. It's K. Right. KLM were the upper bounds. Okay. Now, how about the lower bounds?
Of G, H, J, K.
Lower bounds of GH, GHK. Oh, sorry. GHJ, KLM. GHK, JLM. So I guess you have to imagine, these all being in a set, right?
It's DAB. Yeah.
So it's DAB. And how did you get that?
Because DA and B are the only ones that are related.
That are related to all of them, yeah. Okay.
And D is the greatest.
And the GLB, it's what? So that's the GLB? A GL.
Is
GLB of GH. Tell me again, GH.
K.
Is which element?
D.
D. Find all the lower bounds of HJKLM. All the lower bounds. HJ.
Doesn't H count as the lower bound?
Oh, good point. It can be in the set.
And it is.
And it is. So what are they?
H, D, E, A, B.
H, D, E, A, B. H, D, E, A, B. Yeah, good point. And now what's the GLB? H, J, K, L. I keep wanting to make the same mistake, huh? Is what?
H.
Is H. Is right. Ooh. Yeah? All right. Let's see. Next was, all right, X25. Write the relational table that results from the following queries. Now do you remember what sigma and pi are? Remember we had three, what were the three operations? Sigma is select.
Pi is project.
Pi is project. And what was this?
Join?
Natural join is correct. Yeah?
Yeah.
Okay, so what would happen if we did select
MC, lyrics equals ampersand.
MC, lyrics equals ampersand? So now what was MC?
You would go back to the MC table.
You would go back to the MC table.
And it would return all of the,
So here's the MC table, right?
yeah.
So we want to get this.
And it would return rows? Yes. So it would give us Oklahoma.
But it was for what? Yeah, you select based on a
Lyrics equals Hammerstein.
yeah, on a Boolean. So yeah, lyrics equal, right.
So it would return all the information on the MC table for the shows, right?
Yeah, yeah. And then, okay, so select selects the rows. But on the other hand, what does project do?
It'll give you the column.
Yeah, project projects out a column, the column, right?
So if we did a project on the same thing, which is what B wants us to do.
So in part A, we did a select MC lyrics equals ampersand. This time we're going to project the result that we got from part A, just the title. So that would just be a one column. That would be a one column table, right? Is that right?
Yeah.
So it'd just be a table with Oklahoma and the King and I. One, okay. And then how about where natural join composer, natural join run?
It would give you the title and the theater it was performed in, and the music writer,
Yes,
and how many times it was shown
yes.
for every show.
So it would have title, theater, music, and performance. Perfs. Right? How many columns would there be here?
There'd only be 3.
Yes, there would be 3
And
columns.
there'd be no title, which is the difference between that and C.
Right. There'd be, right.
C would keep the title, right?
Yes. C would keep the title, and D would not have the title. Okay, good deal. And I think, and then, now this was given these questions were given a query, what is the relation? You know, what is the table, the relation as described by the table. The last one, though, is the other way around. It's write a query. Okay, so you have to come up with the, I think you guys all did really well on this one.
Yeah.
I think you can review that on your own. So starting with our next review, we'll start after the relations. Okay. All right, good deal. See you next time.